Welcome back to the Deep Dive. I'm energized today because we are tackling uh, one of the most critical subjects in modern technology. We're looking at the actual, measurable, transformative trajectory of AI, and we're doing it by looking at a really comprehensive stack of recent sources. So we are diving far, far past the surface headlines today. This isn't about some hypothetical tomorrow. It's about what AI is fundamentally reshaping right now. In medicine, in our infrastructure, and even in our cultural landscape. Our listener wants the shortcut, the distilled knowledge, and the insights to be truly well-informed, and that's what we're here to do.
That is exactly the mission. I mean, we have material here that just clearly demonstrates that AI has accelerated way out of a hypothetical phase. It's now actively weaving itself into the very fabric of our society, and in profound and often really unexpected ways. If you think AI is just for chatbots or writing emails, this deep dive is it's going to challenge that perception entirely.
Absolutely. When we started to sort through this substantial body of research and analysis, three massive sort of interconnected themes just jumped out. They really structure our exploration for today. And we're not talking about minor version updates or small tweaks. We are talking about foundational shifts.
Precisely. Foundational is the right word. First, we absolutely have to focus on the undeniable revolution that's happening in healthcare. I'm talking about the precision and the pace that AI brings to diagnostics and drug discovery. This stuff is literally changing patient outcomes on a global scale.
Okay, that's number one.
Right. Second, we have to transition to the engine that's driving all of this, the physical foundation of computation itself. And that means looking at the furious global hardware arms race for specialized AI chips. This race basically dictates the speed and the scale of every single other advancement we're going to talk about.
It's the bedrock.
It is the bedrock. And then finally, we have to address the critical societal pivots, the necessary conversations around ethics, which are heating up, and the surprising high-stakes collision of AI and human creativity, particularly in the world of entertainment.
It is a massive scope, but I think we have to give each area the time it really deserves. So let's unpack this immediately. And let's start with, I think, the most encouraging area, the one with the most immediate human impact. AI revolutionizing healthcare, this new era of precision and pace.
Sounds good. Let's get into it.
So when we dig into the recent studies that we have here, the evidence supporting AI's role in patient care is, frankly, it's overwhelming, specifically through this concept of precision diagnostics. And this idea, it really moves us beyond general medicine. We're talking about tailoring treatment based on an individual's unique data signature.
What's really fascinating here is that the breakthrough isn't just anecdotal. It's not a few cool case studies. It's statistically robust. Researchers have developed AI models that are capable of predicting patient outcomes with what the sources themselves describe as unprecedented accuracy. And that phrase, unprecedented accuracy, it's not hyperbole. It represents a major, major improvement over the existing statistical methods that doctors have been using for decades.
Okay, let's elaborate on that phrase then. Unprecedented accuracy. What does that actually mean in practice? I think we need to explain the mechanism here, the mechanism of accuracy itself. These new AI models are trained by analyzing just absolutely vast data sets.
And when we say vast, we're talking about billions of data points. This is data that's derived from electronic medical records, or EHRs, from genomic sequencing results, and from high-resolution medical imaging. Things like CT scans, MRIs, and pathological slides, basically the entire digital footprint of a patient's health.
Think about the scale of processing that's needed for that. I mean, a human pathologist or a radiologist, they're incredible experts in pattern recognition. That expertise is honed over decades of practice, but they're still limited by time and by the scope of what they've personally seen in their career.
Exactly. An AI system, on the other hand, it can review the collective medical history of millions of similar patients from all across the globe. It can identify these microscopic patterns that are either invisible to the human eye or they're just too subtle for standard statistical software to even notice. This is what allows for that massive leap in predictive capability. It's seeing the forest and the trees down to the cellular level all at once.
So the AI isn't really replacing the doctor here. It's more like it's giving the doctor a superhuman pattern recognition engine. Is that a fair way to put it?
That is a perfect way to put it. The system can connect what seem like totally disparate data points. Maybe a single genomic marker, a minor shift in a blood test from 3 years ago that was ignored, and a subtle change in the texture in a recent scan. It synthesizes all of that into a prediction about disease progression, or a patient's likely response to a specific treatment.
And the sources get really specific about the immediate real-world consequences for the hospitals that are actually incorporating these systems. The first consequence, and maybe the most important, is a documented, measurable reduction in diagnostic errors.
And we can't overstate how big a deal that is. Misdiagnosis is a significant global problem. It costs lives, it costs fortunes, it's a huge source of patient stress. By catching those subtle signs earlier, the AI is acting as this incredibly sophisticated safety net for the clinical team.
And crucially, this translates directly into practical efficiency. We're seeing a significant collapse in the time it takes to get from an initial suspicion to a confirmed diagnosis, and then getting that patient started on treatment.
Right. And for critical conditions like certain aggressive cancers or sepsis, that time is everything. If you can cut the diagnostic cycle from, say, 2 weeks of waiting for biopsies and second opinions down to just a few hours, you are improving patient outcomes dramatically just through speed alone. You're getting ahead of the disease.
The implication here seems enormous. AI is shifting from being just a supportive tool, maybe something a researcher uses, to playing a central, critical role in the actual day-to-day management of disease.
That's the key shift. Because the model can predict outcomes with such high accuracy, doctors can now move beyond these sort of one-size-fits-all standardized protocols. They can tailor treatment regimens immediately. They know with a much greater degree of confidence which specific therapies are most likely to work for this specific individual with their unique biology.
I do wonder, though, how this changes the legal or the ethical framework for the physician. I mean, if a human diagnosis conflicts with the AI's highly accurate prediction, where does the liability lie? Does the doctor have a professional obligation to follow the system that has, as the sources say, unprecedented accuracy?
That's a fascinating and very complex layer that the sources are just beginning to touch upon. The legal systems are, frankly, still trying to catch up, but what is changing rapidly is the standard of care. If the new standard of care incorporates an AI that can spot a specific risk factor with 98% accuracy, a doctor who chooses to ignore that input, without a very compelling and well-documented reason, they could potentially face some serious scrutiny.
So the AI is essentially elevating the baseline expectation of accuracy in the entire field.
Yes. It's pushing medicine away from relying on statistical likelihood for a general population and toward high-confidence precision for the individual. And this transition is forcing hospitals to develop entirely new operational protocols. Protocols that are centered around this human-AI collaboration and, yes, redefining where accountability starts and ends. It's a whole new world.
That makes perfect sense. So this move from population-based medicine, where you treat based on what works for the average patient with these symptoms, to precision diagnostics, focusing on that person's unique biology and history, that is the true quality of care improvement.
It is, and connecting this back to you, the listener, or really anyone who has gone through that stressful loop of a potential misdiagnosis, the months of seeing specialists, the unnecessary and sometimes painful procedures, enhancing that initial diagnostic accuracy short-circuits that entire costly and emotionally draining cycle. It moves the medical journey from a reactive, drawn-out ordeal to a proactive, highly targeted intervention. And that is a massive paradigm shift in the patient experience.
But the revolution doesn't just stop at the diagnosis, does it? It extends directly into creating the cures themselves.
That's right.
Historically, drug development has been a truly lengthy, expensive, and incredibly risky process. We're talking about what people in the industry often call the valley of death in pharma R&D. A compound might look great in the lab, but getting it through clinical trials takes 10, maybe 15 years, and potentially billions of dollars, with a huge failure rate.
That traditional challenge created a massive systemic bias in the industry. It's just a matter of economics. Because the cost and the timeline were so prohibitive, pharmaceutical companies, they focused almost exclusively on widespread diseases with huge patient populations like heart disease or diabetes. The economics just did not support investing billions in solutions for niche or rare diseases, no matter how much suffering was involved.
But now we have the AI solution, which seems to fundamentally rewrite that entire economic equation. The sources outline this new paradigm where AI-driven platforms are, and I'm quoting here, accelerating this journey at scales that were just unthinkable even 5 years ago.
The scale is absolutely the key here. We can break drug discovery down into two major phases where AI is being transformative: hit identification and lead optimization. In the traditional method, hit identification, which is just finding a molecule that might work, involved manually screening thousands of compounds in a lab. It was slow, tedious work. Now, these AI platforms are sifting through literally millions of chemical compounds, modeling their interaction with disease targets virtually, in silico.
So the AI is acting like a highly efficient molecular filter, is that right? Instead of physically testing, say, 100,000 compounds in a lab over several months, the AI can model the potential efficacy and the toxicity of millions of compounds in a virtual environment in just a few days.
That's exactly it. It uses advanced machine learning techniques, often very deep neural networks, that have been trained on these massive databases of chemical properties and biological reactions. It predicts which molecules are most likely to bind effectively with a specific protein target. And just as crucially, it also predicts which ones are most likely to fail later on due to toxicity or poor absorption in the body. This dramatically reduces the number of candidates that you need to physically synthesize and test in a wet lab.
And this acceleration, this is what links directly to that critical social need you mentioned earlier, the ability to finally tackle rare diseases.
It's hugely significant. These rare diseases, which are often genetic or highly specialized conditions, they were previously just overlooked because of limited research funding. And why? Because the upfront cost to research, synthesize, and trial a drug that's designed for only a few thousand patients globally, it just didn't make business sense when the overall failure rate for any new drug was still around 90%.
So AI shifts the economic viability. That's the core of it. By drastically reducing that initial screening time, lowering the costs associated with identifying promising compounds, and shortening the total length of the preclinical phase, AI makes the research investment for these rare diseases much, much more palatable.
It almost democratizes drug development in a way. The traditional economic barrier to entry, that decade-long timeline and that multi-billion-dollar initial investment, it gets softened. And this opens the door for smaller biotech firms, for university labs, for dedicated research initiatives to pursue conditions that were historically just deemed unprofitable by the big players. The implication is profound. Pharmaceutical companies are rapidly embracing these tools, which signals a new era where life-saving drugs could reach the market faster than ever before. This is a fundamental restructuring of R&D from a slow, manual, iterative process to a highly efficient, machine-driven compound identification loop.
So the story of this first section is really clear. AI isn't just optimizing the old processes, it's creating entirely new possibilities for diagnosis and for cures. Possibilities that were simply too complex or too costly to even pursue before.
It is indeed, and those possibilities, those powerful algorithms, well, they are only as good as the infrastructure they run on. Which brings us very neatly to our next section. The algorithms have to live somewhere, and right now the competition to build their home is defining the technological future.
Okay, a perfect transition. We're now moving from the life-saving application layer of AI to its foundational infrastructure. If the algorithms are the brain, then the hardware is the nervous system and the muscle, and we're absolutely witnessing a high-stakes tech battlefield.
I think it's important for the listener to understand that the advancements we just discussed in healthcare, the sifting through millions of chemical compounds, the real-time processing of massive medical images, these tasks are computationally ravenous. They are so demanding, they require orders of magnitude more power than traditional computing tasks, like running a spreadsheet or a web browser. And this realization is what has ignited this global hardware arms race.
The key activity that's identified in our sources is just staggering investment. Major players. And it's not just the traditional chip manufacturers anymore. It's the massive cloud providers and the big tech giants. They are pouring resources into developing more advanced AI chips. And this isn't just about faster clock speeds. It's about fundamentally rethinking the architecture of the chip itself. The singular aim is enhancing the speed and the efficiency of the computations that are required for these modern, complex AI models, especially large language models, the LLMs.
We should probably pause here and explain why the current conventional hardware, like the standard central processing units or CPUs that you'd find in most personal computers, is just insufficient. CPUs are brilliant at serial processing. They handle tasks one after another, sequentially, and they are great generalists. But AI, especially training these massive models, requires massive parallel processing. You have to calculate millions, even billions of mathematical operations all at the same time.
And that's where graphics processing units, or GPUs, they stepped in initially, right? Because their architecture, which was originally designed for rendering video game graphics, naturally excels at doing lots of simple calculations in parallel. But now it seems even the standard off-the-shelf GPUs aren't enough for the most advanced AI tasks.
Exactly. The race is now pushed beyond GPUs into even more specialized accelerators. Things like ASICs, that's application-specific integrated circuits. These are custom-designed chips built to do only one thing: perform the specific mathematical operations that AI models require, and do it with extreme efficiency. They are not generalists at all, they are hyper-specialists.
This also involves a huge investment in memory technology, which is something the sources really emphasize. Memory bandwidth, so how quickly data can be moved to and from the processing cores, is often the real limiting factor in AI training, the real bottleneck. You can have the fastest chip in the world, but if the data can't get to it fast enough, the chip just sits there idle.
Which is precisely why we see such intensive development in technologies like high bandwidth memory or HBM. And this technical detail, it really illustrates the depth of this arms race. It's not just about the silicon architecture, it's about the packaging, the memory, the interconnects, the entire system design working together seamlessly to maximize data throughput for these specific AI workloads.
Okay, let's delve deeper into what these next-generation chips actually enable, because I think we need to distinguish between the two primary uses of AI processing. There's training and there's inference. Training an AI model, teaching it everything it knows, that requires these gigantic, highly efficient data centers. But inference, using the trained model to make a prediction out in the real world, that requires localized speed and efficiency.
The training demands are what drive the absolutely massive investment. Training models like the ones used in accelerating drug discovery or for creating the next generation of LLMs. This can cost hundreds of millions of dollars and take months, consuming colossal amounts of energy. The sources show that companies are just desperate for chips that can reduce that training time and cost, even by a small percentage, because the return on that investment is immediate, and it is huge.
But the sources also focus very heavily on the inference side, providing these specific real-world examples. Let's go back to autonomous vehicles for a second. That vehicle isn't training in real time on the road. It is inferring. It's taking the trained model and using it to make instantaneous decisions about its environment.
And that is where the latency requirements become completely non-negotiable. An autonomous vehicle cannot tolerate a delay of even 100 milliseconds when it's interpreting a pedestrian stepping into the road. These new chips are necessary because they have to process simultaneous inputs from cameras, from LiDAR, from radar all instantly, and translate that data into a decision. A traditional CPU simply lacks the low-latency parallel processing capability to manage that kind of sophisticated, real-time analytics.
So these specialized chips aren't just for data centers anymore. They're for every edge device that needs to operate intelligently and safely. Things like drones, factory robots, and critically autonomous transport. The need for this kind of specialized computation is everywhere that AI decision-making happens.
Absolutely. The need for custom silicon is moving out from the cloud and toward the consumer and industrial edge. And this technological requirement, it's what fuels the intensity of this competitive environment. The chip is the throttle on all AI progress. If you can't run the sophisticated models efficiently, well, then those models simply can't advance.
And this intense pressure has created an environment where companies are, and the sources use this phrase, vying for supremacy in what they explicitly label a tech arms race. This isn't just about market share. It's about controlling the technological baseline of the entire 21st century.
The stakes are incredibly high because the winner of this race, they don't just sell chips, they control the entire ecosystem. If a single company develops a chip architecture that is so efficient that all the major AI researchers and corporate developers standardize on it, that company effectively sets the standard for future AI advancements.
And setting the standard means so much more than just selling hardware, right? It means controlling the software tools, the programming frameworks, the entire optimization pipeline that all the developers use. It creates this incredibly powerful lock-in effect. If your AI model is trained and optimized for one company's architecture, moving it over to a competitor's architecture becomes extremely costly and inefficient.
It's a foundational battle for technological control, and it impacts everyone. From the smallest startup that's building some specific niche application to the massive cloud providers who host the infrastructure for everyone else. The hardware determines the ceiling of capability. If one competitor is limited to a 10 petaflop capability and you have a 100 petaflop chip, you can train models that are simply beyond their reach. It gives you an undeniable, almost insurmountable advantage in development.
This also brings up the geopolitical dimension, which is hinted at pretty strongly in the sources. Controlling the ability to manufacture and supply the most advanced chips is now viewed as a critical national security and economic asset. We're seeing governments prioritize domestic production and control over this highly specialized supply chain.
That is a crucial detail. The race isn't just corporate, it is interstate. It's nation versus nation. Because these chips are the lifeblood of advanced military surveillance and economic AI applications, the production capacity itself is a leveraged strategic asset. If a nation can't access or produce the cutting-edge hardware, its technological future and its ability to compete on the global stage is fundamentally constrained. This just intensifies the competition, and it explains the sheer magnitude of the investment we're seeing globally. It's a battle to build the necessary power source that enables all the transformative AI applications we talked about in healthcare and that we're about to discuss in the realm of culture and ethics.
Okay, so we've established that AI is fundamentally changing how we heal the body and how we build the technological world. It's happening. But as these systems become more powerful, more pervasive, and as the source says, they permeate various aspects of society, the discussion inevitably has to shift. It moves from engineering achievement to human responsibility. We have to confront the societal nexus.
It's completely unavoidable. The hardware race gives us the speed, the healthcare breakthroughs demonstrate the power, but that power demands accountability. When an autonomous system is making high-stakes decisions, whether that's determining a person's credit score, dictating a surgical plan, or deciding who gets paroled from prison, we absolutely must scrutinize the underlying mechanisms and their societal effects.
The source material is remarkably consistent on the core ethical concerns that are dominating the global discussion right now. They seem to center on three words: fairness, transparency, and accountability.
And we should unpack those foundational pillars with the depth they really require. They're not just buzzwords. When we talk about fairness, we are talking about preventing discrimination. It's that simple. AI systems learn from data that's collected in the real world, and the real world, as we know, reflects historical systemic biases. For instance, if an AI is trained on historical loan data where certain minority groups were disproportionately denied loans, the AI will simply learn that denial pattern is correct. It will then amplify that bias in its future decisions, even if the names or other demographic identifiers are removed from the new applications.
So the system isn't maliciously biased on its own. It's just accurately reflecting a historical human bias that's already baked into the training data it learned from.
Precisely. And that's why any ethical guidelines have to compel developers to actively audit their data, mitigate that bias, and reweight the data to correct for it. And this is a monumental task. It's really hard because it requires recognizing and then correcting societal issues through data architecture.
And then there is the challenge of transparency, which is often called the black box problem.
The black box problem is critical to understand. Modern deep learning models are so incredibly complex, with billions or even trillions of parameters, that even the developers who built them often cannot definitively explain why the AI arrived at a specific decision. For example, why did the AI recommend this treatment path over another one? What was the key factor? Transparency means we need model interpretability. We need tools that can peek inside that black box and tell us which specific input features, which data points, were the most influential in making that final decision.
And why is that level of transparency so essential? Why can't we just trust it if it's accurate?
Because without it, you can't have the third pillar. Accountability. It's impossible. If an AI error occurs, let's say an autonomous vehicle causes a collision or a diagnostic tool recommends a harmful treatment, who is responsible? Is it the developer who trained the model, the hospital that deployed it, the doctor who followed its recommendation?
Accountability requires traceability. You have to be able to trace the decision back to the input data and the decision-making logic, and that demands transparency. You can't have one without the other.
The response that's outlined in the sources seems to be global and highly collaborative. It's not just one country. Organizations and governments are actively collaborating to draft ethical guidelines. And this isn't just academic theorizing. This is real legislative and policy work.
And that collaboration is key because AI and the data it uses doesn't recognize national borders. The purpose is straightforward, but absolutely massive, to ensure that these technologies are developed and deployed responsibly. The guidelines are being designed to create a baseline of trust, because if the public doesn't trust that AI systems are fair and accountable, then adoption, even for the life-saving applications we talked about, will stall. People will reject it.
The concrete goals seem to be preventing bias, which we've discussed, and also protecting individual privacy, which is a huge concern considering the massive medical and personal data sets that are being used for training.
Protecting privacy is another tightrope walk. It's a real dilemma. The more data you feed the AI, the more accurate and powerful it becomes. That's just a fact. But that powerful performance comes at the cost of gathering highly sensitive individual information. So the regulatory challenge is finding a way to allow for the vast data aggregation needed for powerful AI training, perhaps through advanced anonymization or synthetic data generation, while ensuring that individual rights remain absolutely protected.
This really raises the fundamental question that sits at the center of all the sources on this topic. How do we achieve a balanced approach where innovation does not come at the cost of ethical considerations? It seems like regulating without stifling progress is the ultimate paradox here.
It is the ultimate tightrope walk, no question. If regulation is too heavy-handed, or if it moves too slowly, it risks halting the very innovation that is curing rare diseases and creating safer transportation systems. But if it's too light, we risk amplifying societal inequalities and creating these unaccountable black boxes that cause real harm without any recourse for the victims. The collaborative effort we're seeing suggests that the global industry understands this. They know that responsible innovation, guided by clear ethical standards, is the only sustainable path forward. They seem to be aiming for enforceable standards that civilize the technology, not outright prohibit it.
Okay, let's shift gears entirely now. We're moving from the governance of AI to the culture of AI. This is where the technology moves from being a highly functional tool to something that actively challenges our very definition of human expression. Let's look at AI in entertainment, creativity, and collaboration. The sources are all highlighting the truly rising sophistication of AI-generated content.
The sheer capability is, well, it's astonishing. We are far past the early, clunky, sort of weird-looking phases of AI art. We are now seeing algorithms that are capable of creating music compositions that evoke complex emotional responses, generating visual art that can pass for human mastery, and even drafting full-length, complex screenplays that adhere to classic structural narrative rules.
What really stands out here is the ensuing cultural debate that this capability has spurred. I mean, if a machine composes a soundtrack that makes an entire movie audience cry, is that a creative act? If an AI writes a novel, does it possess originality, or is it just a very sophisticated remix of its massive training set?
These questions are deeply philosophical, but they also have immediate economic and legal ramifications, primarily around intellectual property and copyright law. Traditionally, creativity implies human intentionality. A human had an idea and executed it. Now we have machine output that bypasses that intention, and it's forcing legal bodies and artistic institutions to grapple with the idea of ownership. Does the human who wrote the prompt for the AI own the result? Does the company that trained the model own a piece of it? Or is the output simply uncopyrightable in the public domain?
I do wonder, though, if the debate focuses a little too much on replacement and not enough on augmentation. Does the source material suggest that AI is taking jobs from artists, or is it changing the definition of the job itself?
That is where the collaborative angle really comes in. The sources point very strongly to the potential for AI to collaborate with human artists in new and exciting ways. Think of a film director, for example. Instead of spending months with a concept artist to design a visual world, they could input a script and have an AI generate 1,000 high-resolution concept images in an hour. The human artist's job then shifts from the manual execution to high-level curation, selection, and ideological direction. They become the tastemaker.
Yeah, so the human is the editor and the curator of the machine's output, rather than the original generator of every single element from scratch. It completely shifts the entire creative workflow.
Exactly. And that analysis aligns perfectly with the observation in the sources about the blurring of lines. AI is moving beyond just being a sophisticated tool, like a better paintbrush or a new synthesizer. The sources suggest it is becoming a creative partner. It's actively contributing compositional ideas, structural suggestions, and variations at a scale no human could match. For a composer, the AI might generate millions of melodic variations on a single theme. The human then selects the one that has the necessary emotional resonance for the scene.
This signifies a genuine cultural shift. We're seeing the very definition of creativity being challenged and redefined by machine output that can meet established aesthetic and narrative standards. It forces us to ask, if art is about its impact on the audience, does the source of the creation, human or machine, truly matter to the person experiencing it?
And for entertainment producers, the efficiency is just undeniable. It allows for rapid prototyping of ideas, personalization of content for individual viewers, and the creation of content at volumes that were previously completely unachievable. This collaboration element means the future of artistic production is increasingly going to be a hybrid of human and machine, and the cultural implications of that, well, they're only just beginning to unfold.
This deep dive has spanned the entire spectrum of AI's current impact. It's really incredible to lay it all out. We started in healthcare, where the accuracy of precision diagnostics and the accelerated development of new drugs are already saving and improving lives on a global scale. We then transitioned to the invisible but absolutely essential foundation, the hardware arms race. That furious competition for next-generation AI chips that really determines the speed and the limits of all other advancements, from autonomous vehicles to massive data centers. And then finally, we explored the societal nexus, grappling with the necessity of ethical guidelines around fairness and accountability, and the fascinating disruptive role of AI as a creative partner in the arts.
What defines this moment, and this is clear across all the sources, is the pace, the sheer velocity of it. AI is not advancing incrementally anymore. It is accelerating exponentially across all of these sectors at once. The pace of change, from life science innovation to pure creative production, is fundamentally constrained and defined by this powerful duality. You have the ever-increasing capability of the new specialized hardware on one side and the essential constraint of robust ethical governance on the other. It's a dynamic tension between velocity and responsibility.
And it is in that tension that the most profound and probably the most challenging developments will continue to occur.
If we connect all of this to the bigger picture for you, you've seen the proven capability of AI to tackle problems that were previously thought to be intractable. Complex, high failure rate issues like drug discovery for rare diseases, and the deeply nuanced subjective challenge of high-level creative production. AI excels where human cost, time, or complexity had previously erected an insurmountable barrier.
Which leads us to a final provocative thought that we really want to encourage you to keep exploring long after this deep dive ends.
Given this new baseline capability for AI to solve these overlooked high-complexity, high-cost problems, the ones that didn't meet the traditional economic or logistical viability test, what unexpected rare human endeavor currently ignored or deemed too difficult due to its inherent complexity or its massive cost will AI tackle next? Will it be climate modeling at a molecular level, or maybe solving the logistical nightmare of interstellar communication? What massive overlooked problem will AI suddenly make viable? That is the question we want to leave with you.
Thank you for joining us on this deep dive into the truly transformative landscape of artificial intelligence. We will catch you next time.